In this video, we will be learning how to calculate mass percent composition. As part of our learning objective, we're learning how to calculate the percent composition of a compound. So the definition of any percentage is how much does a part contribute to a whole. And so that's percentages are always out of 100 as per the name. So it says out of 100. So if there were 100 pieces of the whole, then how many of that one part or component do you have? And so when we're talking about mass percent composition of a particular compound or substance, we are talking about how much does the mass of one element contribute to the mass of the whole compound. You can determine the mass percent composition based on molar masses from the periodic table, and you can also calculate them from experimental values. And so we'll do some of each. So this first example involves mass percent composition from experimental data. And so this one tells us that we have a compound contains nitrogen and oxygen, and it has 1.52 grams of nitrogen and 3.47 grams of oxygen. Determine its percent composition. So we do not know the chemical formula, and so therefore we can't use the molar masses from the periodic table. We have to use the mass of the experimental values given. And so the percent due to nitrogen would be equal to the mass of nitrogen over the total mass of the compound. Now, we know that the whole compound is made out of nitrogen and oxygen. So whatever that is, we would multiply by 100. And so the mass of nitrogen was 1.52 grams, and the total mass of the compound would be due to nitrogen and oxygen. So we're gonna have to add those together. And then multiply by 100 in order to get the percentage. And so in my calculator, that would be 1.52 divided by, and then I'll open up parentheses to communicate to my calculator that both of those are in the denominator. And then I have to multiply by 100 to turn that into a percentage. So if you use a percent button or on your calculator, then your calculator treats 100% with a percent sign as 1. And so to turn that decimal into a percentage, here, I'll show you what it looked like before. So if you don't type in, oh gosh, why is it not? No. Okay. So if you don't type in the times 100, then that looks like 10%, or it looks way less. What am I doing? What was I going to say? Oh, you know what? That's why it looks low. I didn't type in 1.52. I typed in, come on, stupid thing, delete the 0. There we go. That looks more right. It's like, why does it only look like 10%? It should looks like more. And then as far as sig figs go, this, when added together, would be significant to the hundredths place. And so both the numerator and the denominator would have 3 sig figs. So that's 1, 2, 3, 30.5% nitrogen. Then my percent due to oxygen would be the same, only inversed. So that's 3.47 grams divided by 1.52 plus 3.47 grams. And let's see if I can type this into my calculator correctly the first time. And so that's 3.47 divided by open parentheses 1.52 plus 3.47. And so you can see here that looks like 0.69 because I haven't typed in times 100. And so when I do the times 100, turn that into percentage, then that 0.69 is 69.53907%. And my sig figs will be similar. That's 3 sig figs. That added together would be the hundredths place, and then that would be 3 sig figs as well. And so that is 69.5% oxygen. And then as a double check to myself, these should add to a 100. And they do. More precisely, the unrounded number should add to 100. Once you round for sig figs, it might add to like 99.9 or 100.1 or something close to 100, but not quite 100. All right, here's another example from molar mass. And so the problem just reads, calculate the percent composition for hydrosulfuric acid. So before I can calculate the mass percent composition, I have to figure out what hydrosulfuric acid is, the chemical formula for it. So hydrosulfuric, hydro would be used for binary acid. So this is a binary acid. So I'm going to need sulfur. Sulfur forms 2 minus ions. And so I'm going to need 2 hydrogen ions to make that neutral. So my chemical formula is H2S. So now I can calculate the percent due to hydrogen and the percent due to sulfur. And so the percent due to hydrogen would be due to 2 hydrogens. So that'd be 2 times 1.008 grams per mole over the mass of the full thing. And I haven't calculated the mass of the full thing yet, so I'm just going to calculate it as part of my calculation here. And so I would need 1 sulfur and 2 hydrogens in the whole thing. And so then I would take this and multiply it by 100 to turn that into a percentage. And so, backwards. Oh, screw it. Okay, I hit clear. So my numerator is 2 times 1.008, and my denominator is 2 times 1.008 plus 32.06. And then I will turn that into a percentage. And so that is 5.916. Why is my 6 so little? And all of these had 4 sig figs, and so most likely I'll end up with 4 sig figs in the end. Grams per mole. No, not grams per mole. Percent. The grams per mole cancels out. Grams per mole divided by grams per mole is just nothing. Okay. Now for sulfur, 32.06 grams per mole. And one disadvantage of not actually calculating the denominator from above is that I have to re-enter the whole thing again. Always write your units on values so that you can make sure that you are ending in the unit you think you're ending up in. And so I have 32.06, and that's going to be 2 times 1.008 plus 32.06, and then I multiply that by 100, and 94.08%. Both of those have 4 sig figs, and so that is fine. And I can double check that my previous answer, let's see if I can grab the previous answer. Nope. Okay, I'll learn how to work this calculator better eventually. But in most calculators, you would be able to scroll back and grab previous numbers to double check that they do add to 100. But mine look like they do-ish. So we're good. Okay. Your answers might vary slightly depending on which molar masses were on the periodic table you looked at. Here's a practice problem for you. Go ahead and try to pause the video and in your notes work out what mass percent of zinc chloride is due to chlorine. Unpause the video when you are ready to continue. Okay, so before we can begin, we have to get our chemical formula for zinc chloride. Zinc is a metal, chlorine is a nonmetal, so this is an ionic compound. Zinc has a common ion charge of 2+. Chlorine has a common ion charge of 2-. So I'm going to need 2 chlorines to make that neutral. That's CnCl2. So the mass percent due to chlorine is going to be due to 2 chlorines. And so we'll use the molar masses since we were not given any experimental values. 35.45 grams per mole. And then out of the total, which is 1 zinc, that's not what zinc is. Zinc is 65.39 grams per mole plus my 2 chlorines. And so now I got to type that into my calculator. So bust out the nice parentheses. 2 times 35.45 divided by 65.39 plus 2 times 35.45. Make sure that matches what I tried to type in before. It looks good. Multiply that by 100, and then that would end up 52.0214%. Everything here had 4 sig figs, and so even if this denominator added up to more than 100, the numerator would still have 4 sig figs, and so my answer would still have 4 sig figs. So I'm going to say 52.02% by mass chlorine. I could get more sig figs by using better periodic tables. Okay, mass percent can also be used as a conversion factor in math. So this is an example problem where that will happen. This problem reads, carbon dioxide is 72.71% by mass oxygen. How many grams of carbon dioxide contains 10 grams of oxygen? So let's go ahead and write out what we're given. We are given 10.0 grams of oxygen, and we are asked to find how many grams of CO2. And so we are asked about different compounds, and so we could go to moles in order to work out a relationship between the subscripts here, or we can use the mass percent composition that's given to us. And so that's the route we're going to go today. How this works, though, is this conversion factor here says that for every 72.17 grams of oxygen, that's out of 100 grams of carbon dioxide, because percentages are always out of 100. So if I had 100 grams, 72.71 grams of that would be oxygen. And so since that numerator was 4 sig figs, I'll go ahead and have 4 sig figs in the denominator as well. So I wrote that out as a conversion factor so that we can make sure that we're canceling out our units appropriately. This was grams of oxygen, and so my denominator needs to be grams of oxygen in order to cancel that out. Then my numerator would have to be grams of carbon dioxide. And so my grams of oxygen was the 72.71 number. And percentages are of 100, and so that 100 goes there. So I have 10.00 times 100 over 72.71. And so that tells me that I would need 13.753 grams of CO2. That's 1, 2, 3, 4 sig figs, 13.75 grams of CO2. So just as a conceptual double check, the mass of the whole compound should be more than the mass of the individual component. Or in other words, the mass of a component should be less than the mass of the total. Because we know that the mass of carbon would have to be added to that 10 grams in order to get up to 13.75 grams. So that's a good double check to make sure that you have your conversion factor set up correctly. All right, here's a practice problem for you. It reads, what mass of water would 25 grams of copper sulfate heptahydrate contain? Go ahead and pause the video and try to work this out on your own. Unpause the video when you are ready to continue. Okay, let's work this out. We are not given any information, so we're going to have to use molar masses in order to work this out. But we can take our 25 grams and multiply that by the mass percent composition due to water in order to work out what mass is due to water. So the first thing we're going to do is calculate mass percent composition based on molar masses. And then we'll multiply that by the 25 grams. So let's work out the mass percent composition based on molar masses. So my percent due to H2O would be equal to my mass of 7 waters. Each water contains 2 hydrogens, 1.008 grams per mole. And then I have 1 oxygen, so that's 15.999. And then I have to work out the copper sulfate heptahydrate. Copper is 63.55 grams per mole. Only one of those. One sulfur, so that's 32.06 grams per mole. And then I have 4 waters, or no, not 4 waters, 4 oxygens, 15.999 grams per mole. And then I also have my 14 hydrogens due to the water. And then that is 7 waters, 7 oxygens again. And then I would take the whole thing and I would multiply by 100 in order to work that out. So my percent due to H2O is equal to 7 open parentheses 2 times 1.008 plus 15.999. So that's telling me that I have 7 waters. Now I need the mass of the whole thing, 63.55 plus 32.06 plus 4 times 15.999 plus 14 times 1.008 plus 7 times 15.999, and then I'd multiply by 100. And so that tells me that I am 44.1372% by mass H2O. And then I never want my molar masses to limit my sig figs, and so I'm not going to worry about rounding here. It does look like all my molar masses are at least 4 sig figs, and this is 4 sig figs. So I'm fairly certain my molar masses would not limit my sig figs here, and if they did, I would have to just use the better periodic table, because molar masses should never limit your sig figs. So if I have 25 grams of the compound, I'm just going to call this hydrate. So if I have 25 grams of my hydrate, I will have to cancel out my grams of hydrate. And then end up with my grams of H2O. And so for every 100 grams of my hydrate, I will have 44.1372 grams of water. And so that is 25 times, so 25.00. Nope, that's not the right button. Try and do the second answer, but my pen mistyped. My answer from before times 100. So 11.0343 grams H2O. This has 1, 2, 3, 4 sig figs. So this has 1, 2, 3, 4 sig figs. 11.03 grams of H2O. So just to double check that this makes sense, this says that 44% is a little bit less than half. And so half of 25 is 12.5. And so I should have a little bit less than 12.5, and I do. So that kind of tells me that I did grab the right number in my calculator when I hit the previous answer button. and 11 is less than 25, so we're good. Okay. That concludes our mass percent composition video. And in our next videos, we will be learning about empirical formula and molecular formulas from mass percent composition.